All right, so this is the second half of part 1 from chapter 16. So we want to calculate the pH of a 0.3 molar solution of acetic acid. So the formula for acetic acid would be that. So, and we know the Ka has already been determined. So in order to find the pH, we have to know how much of that acetic acid actually splits apart into the hydronium ion, because that's what we need to know in order to measure pH. So you just have a series of steps to solve this sort of problem. First thing is we want to write the reaction. So acetic acid, or whatever your acid is always going to be added to water. It's going to give a hydrogen away to the water to turn into the hydronium ion. And then what's left is our conjugate base. 3O2. Now if you want to abbreviate this as just HA, and this is just A minus, A meaning whatever your conjugate base is, you can also do that. Okay, our Ka expression is going to be equal to our products over reactants, but again we do not put water in there since that's part of the Ka already. So our goal is going to be to figure out what this value is, and that's how we can figure out what the pH is. Okay? So in order to do all of these equilibrium reactions, we have to do an icebox. So this one didn't even include water at all. You can just ignore it completely. So our initial concentration was 0.3 of our two products. Initially is 0. This goes down by 1 mole, up by one X number of moles, and then up by X number of moles. Okay. Then we're going to plug those equilibrium expressions into our K equation. So just to rewrite what that was. So we know Ka because it was given to us in our problem. It's 1.7 times 10 to the negative fifth. Both of these are x, so we can rewrite that as x times x, or x squared. And then our HA was 0.3 minus x. We can put that on the denominator. Now, in order to solve this, you would have to use a quadratic. So what we want to see is if we can avoid that by doing a simplification. So what we want to do is see if Ca over Ka is greater than 100. Ca is our initial concentration of acid. Ka, also known. So when we do that, we get about 17,000 roughly. So yes, it is greater than 100. So that means is we can ignore this minus x completely, because whatever x is, it's not going to change 0.3 to anything else. Okay. So now our K expression is much simpler to solve. And now we can solve for x. So multiply both sides by 0.3, take the square root, and if we go back to what x actually stands for, x is going to be what H3O plus is. So now that we know what H3O plus is, we can find the pH. And of course, H plus and H3O plus are equivalent, so they're the same. So in this case, pH is 2.65. And remember, we can check to see if this kind of makes sense logically. Acids have a pH of less than 7, so that holds true. And we know this is a weaker acid, so it should be something greater than 2. Okay, so we already have a good assumption that your x is less than 0.3 using that check here, where when we divided them we got 17,000, so we can already assume that x is going to be small. You can also check by finding the percent ionization. So the percent ionization starts with the degree of ionization. So degree of ionization is your amount of H3O plus over your starting amount of acid. So 2.3 times 10 to the negative third over my starting concentration, which was 0.3. So when we do that, we get 0.0077. Multiply that by 100 to make it a percent. So yes, it ends up being less than 5%. And that is another way to verify that we can make that assumption of ignoring that minus x. Okay. Now, you could have also solved using the quadratic. It's just more work, so we can avoid that if we can, obviously. But you're going to get the same answer. Now, let's say we have a same concentration, 0.3, but of a strong acid instead. So strong acids completely dissociate. So if we have 0.3 molarity of that, that means we also have 0.3 molarity of our H3O+. Which means solving for pH is much more simple. You don't have to do the icebox. You can just plug it in straight away into your formula, which you get 0.52. Which again should make sense because a strong acid is going to have more ionized, which means you're going to have a lower pH. So again, stronger acids should have a lower pH. And so this one was 3.52 versus 2.6. So again, it makes sense based on the math. All right. What is the pH of a solution that has 0.325 of acetyl salicylic acid, which is just aspirin, and 0.5 liters of water? The monoprotic acid, and we know the Ka. So first thing you have to do is find the concentration of your aspirin. Molarity is found by doing moles over liters. So you have to change this to moles. The molar mass has been given to you, so it's a little easier. And then divide it by your volume to get the concentration. So when you do that, the concentration of your HA is 3.6 times 10 to the negative third to start. All right, so we have our equilibrium reaction. We're going to ignore water. Our acid concentration we just solved. Initial products are 0. These go down by some number of moles, up by some number of moles, so we can find our equilibrium expressions. Okay. Our equilibrium expression, our Ka expression, is going to be equal to, in this case, our conjugate acid over our starting acid. Both of these are x, so x times x is x squared. And then HA, 3.6 times 10 to the negative third minus x. So we want to see if we can avoid this minus x by checking for our simplification. Is Ca over Ka greater than 100? So our initial concentration, 3.6 times 10 to the negative third. Ka is 3.3 times 10 to the negative fourth. This is approximately 11, which means it is not bigger than 100, which means you cannot ignore this minus x. Whatever x is, when you subtract it, is going to significantly change the denominator. So, which means in order to solve this, we have to use a quadratic. So it's the same idea as chapter 14. You would want to multiply both sides by your denominator, distribute your 3.3 value to everything, get it into the quadratic setup, which would be ax squared plus bx plus c is equal to 0, and then solve for x using the quadratic formula. So when you do that, you get two possible values for x. And if we look, the second option is negative, and we can't have a negative concentration, which means we can ignore this one. We know that this one is the one that is incorrect. So X in this case, we have solved for, which is also going to be equal to our H3O plus, which means now we can solve for the pH. So when we solve for the pH, we get roughly 3.03. All right, one more example. What's the pH of a 0.250 solution of formic acid, which has this formula and our Ka? So step one, again, is going to be to write your reaction. I'm going to abbreviate it as HA. And to do your icebox. Plus X plus X. So ICE. Step two is going to be to plug that into a K expression for your reaction. X times X is going to be X squared. Step three is going to check for the simplification. So is Ca, which is 0.250, your concentration you start with, over your Ka, is that greater than 100? Now normally you can tell just by kind of looking at the values, but it's never a bad idea to actually solve for them. So we get 1470, yes. So now we can solve for X with that simplification. So in this case, X is going to be equal to 6.5 times 10 to the negative third, which again is going to be equal to our H3O plus. So then finally, we can solve for pH. Some problems might ask you to also find the degree of ionization or the percent ionization, which you could also do, 2.2. The degree of ionization is going to be how much acid you have, which is your X value, over your starting concentration, which was 0.250. Your percent ionization is going to be that times 100, so 2.6%. So those are sort of the basic setup, the kind of 5 steps you're going to have solving these different problems, either solving for Ka, solving for H3O+, solving for pH.